Thank you.
Okay. Thank you, Hussein. Thank you for the opportunity. So this talk is, the motivation of this talk is twofold. First is to discuss a little bit on things that we tell often the users of our system to use modern techniques for testing the software, and we don't use those techniques ourselves. So this is first to give them an example on how they should write software and how they should test. So we have this framework that will help us testing the deployment of the software. And also the other motivation is to share all the hard work that we had before we started working with EasyBuild and after. So we would like you to be able to reuse the work that we did. So the second motivation to do this talk is to share all the work that we did in the hope that you can reuse and then join the community. So these are the two main motivations for this talk. So the text is not like I expected, but I'll try to go on anyway. So yeah, I have a problem on the slide. So the table of contents is not okay. So I will just tell you first, I will give you a background on the problems when managing scientific software stacks. So Massimiliano have already gave you a good background, so I don't need to spend a long time with that. Then I will show you the use cases where we have at CSCS this setup, and together with a short explanation of EasyBuild. So EasyBuild has already been presented here, so I won't be giving a technical talk on EasyBuild because it has already been presented here. You can find on the web. I will just be explaining how we use it at CSCS, and I will just explain you the main concepts, and I won't be giving you the full details because it has already been done last year, so, and you can find on the web. So the main issues when installing and managing a scientific software stack at scale are that the scientific software has many dependencies, and they need specific versions of the dependencies, and they need several compilers. I think Massimiliano was very clear at this point. The other problem is that we have very long compile times that at some point it needs some manual intervention. So it's not just you set up everything and the computer does the build. You need to be there to watch if it fails at some point, or if it asks you a question. You find software that are packaged in many different ways, so it's always a surprise what you find when you're building scientific software. So this is very time consuming. Just to give an example, when we have an operational system upgrade, we need to rebuild everything. And this is something that could take 1 month of our team if we just do that manually. So the interest of using an automated mechanism is here. So the other problem we have is that the recipes are scattered, meaning that people are working on their own scratch space, and then in the end, if the person who built the software is not there, it's not easy to find where the people was working, and then to find the recipe if the person is not there to point you out. This is my recipe. If you want to redo it, this is how you do it. So, and every person has a different way of writing the recipe. So if a different person takes the recipe of someone, it's not 100% sure that it will work, because everyone has a different way of working. So this is a problem. The other problem is that there's little collaboration among HPC centers, meaning that everyone is working on their recipes on their sides. This happens very often. So if you want to see how other sites are working, you need to go and ask them, how are you doing that? How are you building this software? So it's not transparent. Every time you build something, it's not automatically visible to the community. So we need to ask people to share, and it's not really easy and transparent. The other problem is the reproducibility. So the default base software that you have on the system might change from the time where you build the first time and the second time. So this leads to problems with API compatibility, but sometimes it's even more complex. So whenever you just build something and you don't pin the dependencies in the future, you might try to rebuild, but if you use other software version that you didn't expect to. So here's just, I presented a list of problems, and now before starting the talk, I wanted just to highlight the solutions that we use at CSCS. So for the complex dependency list, we propose to use a framework with dependency resolution, so you don't go and fetch the dependencies manually, you just use a framework that does that. So that's EasyBuild. For the time-consuming problem is the same. We need a framework that allows you to automate the builds, that it will answer yes after 30 minutes of build, and you don't need to be in front of the computer. And for the problem of having non-uniform and scattered build recipes, we propose to use a Git repository to store all the recipes. The same for the collaboration among the HPC centers. We propose to use a collaborative online platform as Github, so we have all of our recipes available on the internet, and we hope that other sites will start doing that so that we can share recipes. And for the reproducibility problems, we advise and we use pinned version numbers for all the dependencies. So we don't use the default software available on the system. We always say that if we want a specific version of MPI or GCC, we say that we want that version, and we don't use the system default to avoid that in the future this default will change and the build will fail. So the possible approaches for automating builds for HPC. So the most common option on HPC is to build software from scratch, with the advantage that you have the software that is optimized for your architecture and for the interconnect. The problem, as I said already, is the long build times and the differences that you might have in the OS dependencies, because software was developed in one operational system, you move to another, and then it might fail, and then you need to fix. So the best examples for that software that can help you with that are EasyBuild and Spec today for HPC, and we have also some projects that are working in providing pre-compiled binaries and using containers to isolate the OS dependencies. So we have people at CSCS working with this kind of solution. We, as application support team, we think that this is the solution for the future, but to say that the reality right now is that our systems are not yet ready to run this kind of solution for all the users, so we still prefer to build software from scratch. Going to some concepts about what I'm about to present here. So continuous integration and testing is often used in software development, and here we want to apply it also to software deployment. The idea of the continuous integration and the motivation is to early detect problems in the system. So we can do that by always building software or testing our deployments continuously. So we run tests from time to time, and then, or regularly, it's better to rephrase like that, and then whenever there's a change in the system, we know very early. So whenever there's a change in the programming environment that affects our builds, we don't wait 6 months to find out that there's one software failing. We rebuild at CSCS all of our software stack every week, so we know that our programming environment is always sane. And this can be extended to continuous delivery. We are working on that. We have a project called Reframe that we are working on the regression testing. And the idea is to, on top of building the software, we are also doing performance and also testing the correctness of scientific software automatically. So the continuous testing is useful for the same reasons, is that we have early feedback for if you have problems, and also whenever you're testing a new contribution with continuous testing, you can quickly know if our contribution is working or not with the current system. So here I just put a list of popular tools that you can use for that. At CSCS, we use Jenkins, but you could use Travis, C-Dash, Bamboo, or GitLab CI. So the third part for the concept, so it's the collaborative development tools. What is the advantage of using this kind of tools also for deployment? So most people here, I think you know GitHub already, and it's mostly used for development of software, but it can be readily applied also for deployment. So we have the versioning of distributed versioning system, so you have revision control of your recipes. Whenever you add a recipe, you know who added, when, and so on. And on these collaborative tools, you have also bug tracking, feature requests, task management, and wikis. So this all helps us to manage the builds. And the one important thing that this platform adds is the ability to do pull or merge requests depending on the platform. And this is very important to add co-review. So this is a key element if you want to have production software, a high-quality production software. Having people reviewing other people's code is the same concept we have in software development. We can use directly here for code deployment. So whenever one person proposes a new recipe, then someone else should go there and review. So to have 4 eyes, it's always better to spot problems. So, and it also can integrate with CI tools such as Jenkins, Bamboo, and so on. So going to the second part of the talk. So as I said, EasyBuild has already been presented here. I won't go into all the details. I go to the high-level presentation of the framework. So since we just had the talk on Spec, I would say it's a very similar tool as Spec. I will highlight the difference. Highlight the difference after, and then so it's a framework for installing scientific software on HPC. It is implemented in Python. It started in 2009 in Ghent, Belgium, and is open to the open source community since 2012. It has a stable release cycle. It's very short, so 2 months in average. It supports today more than 1,000 different software packages. Here is just a few of them, and then I give you the link to the documentation if you're interested in learning more. So the future highlights are that you can fully and autonomously install scientific software. Here it says not only, because also the dependencies are taken care, and sometimes they are not scientific, but you need to have them as well. So you have login on everything. So every time you do a build, you get the log file somewhere inside the build file. You have archiving of the build specifications, meaning the recipe. So every time you build something with EasyBuild, you just go to the software folder and you can find the recipe. Anyone can go inside, find the recipe, and rebuild the software. You don't need to talk to the person who did it to find out, so this is one advantage. It is highly configurable in the sense that you have many config files or environment options or command line options, so you choose. You can extend dynamically by writing new easy blocks, which are pieces of Python code or tool chains. Reproducibility is one of the main goals of the framework. So that's why EasyBuild just don't use. Typically, we don't use the compilers from the system. We build a layer on top of that to make sure that we isolate somehow, whenever possible, the OS dependencies with the software dependencies, so that everyone installing in different systems, at least they can have a layer that will isolate from any differences that come from the operational system. So it has been comprehensive tested, so it has unit testing, regression testing. As I said, we tell users from our system to do that. So also this framework is doing that, and before releasing a version, they don't build all the recipes because this is prohibitive. The cost is prohibitive for that, but there's a selected test of builds that are done before every release. At CSCS, we update every release. We use the stable version from the website, and so far, since 1.5 years, we have only a couple of regressions, so it's pretty stable in that sense, and we can stay on the stable branch. So you have transparency, so it's not a black box. At first, of course, if you run for the first time, you don't know what is happening, but you can use dry run so that it will show you the commands that it is running. And you can also go at the logs to see what EasyBuild is doing whenever you're doing a build. So this slide is just to show you that there's a growing community. So it's this is an effort that from many people. I don't have the numbers of contributors, but you can see from the curve that the interest is growing. We have many sites already in production. We heard already this morning of artists, and we know that other industrial partners are using, so this is not a new software that it's just tested on a couple of universities. This is really used in production since many years. Now I'm going to explain the main terminology so that you understand which part of the framework and I'm referring to. So the framework itself is just it's the core of EasyBuild. It's all the modules that help us to build and install software. So also to create module files, to download the software, check check if the download files are correct. Then the easy block are the Python modules that will implement a generic software build, so you don't need to implement a Python code for every application. You can have generic Python codes, and then on top of that, you create an easy config files where you're going to give the specific version and the dependencies and the versions of the dependencies for each software. So the easy config file is not really Python code. It is Python, but it's not like you need to program Python to create that. And the tool chain is a set of compilers and numerical libraries that is used in order to at least have a basic working environment for doing scientific work. So at least MPI and BLAS and LAPACK typically. So I'm adding one slide. This is not to start a flame war with Spec. It's just to have some context. And of course, my view is biased by my previous work. But I think these are, it's important for you to understand where the two projects are different, and then to choose yourself which one fits you best. So the main focus from EasyBuild, it's HPC systems. So it has a smooth, and this is very stable. The integration with environment modules is something that it has been there since a long time. Spec, it's multi-platform, so the goals are more ambitious, I would say, like that. And just to give an example, the module support is not the standard way, the default way of using Spec. Also because it is not designed only to HPC, so it makes sense on there. Reproducibility. So as I said, EasyBuild pins all the versions, so the recipes are made to be shared and to be reproduced by other users as is. So it's not to make generic recipes that might work for you or not, depending on the version that you pick. The versions are there for one reason. We pin the versions everywhere because you want anyone to be able to reproduce that build. People spend hours trying to figure out if a build will work or not. So whenever we have an easy config file, it means that someone spent time on creating that configuration file and the build file. So it has a sense. While Spec gives you more flexibility, so you don't need to add versions to all of the builds. And the other thing that it is very good is to use the system compiler. So if that suits your use case, then I would say that EasyBuild has more points here because Spec has more points here because you can just go to the system and Spec will inspect the system and tell which compilers he's able to use, while EasyBuild is really I would say static set of compilers and versions that you should reuse. So it's based on popularity. You have a recipe with popular compilers and MPI version, then people will just reuse the popular one. That's the idea. So the stability, I would say, is a plus for EasyBuild, since it has been used in production since many years, even before Spec was born. So the popular toolchains are validated worldwide, meaning that people that use popular versions of toolchains, they are testing everywhere. So after every release, if there's a bug, in 1 second after the release, there are reports. So in that sense, if you're using the popular toolchains, you're on the safe side. While Spec, that's my view, it's more bleeding edge, it has more features, but in the other hand, it has less releases. So for the people that I have contact with, they have their own branch to work on production, because the stable one is updated. Whenever you have a problem on Spec, they tell you to move to the latest development version because it is already fixed on the development. So it's not for production. I would say it still needs some time, at least, to be considered for large-scale production. So
yeah, it's just used at 11 and
yeah. So this is just as Massimiliano said. They have many people contributing to new features on Spec, on EasyBuild as well. We have many people, but I have to say that for us at CSCS, this is the summary of all of my commits on the framework. So it means I'm not really a contributor of EasyBuild. We just everything that it was there, we just reused. I didn't have to touch the framework. So this is what I meant by production ready. Yeah, we managed to make it on production with only really minor changes to the framework. Another advantage of Spec, it can be used as spec manager, as while EasyBuild only create modules and then you need to manually delete files. Main limitations of EasyBuild, so how do I use, this is a FAQ, how do I use a compiler and MPI combination that is not available already on EasyBuild? Then this means that if it's not there, if you start with EasyBuild and your combination of compiler and the MPI version is not there, it means that it will take you a lot of time to bootstrap and to start. While on Spec, this is straightforward to use any combination that you wish, straightforward. Another issue is the number of easyconfig files that grows too fast because of the pinning of versions, so this is a choice. You cannot have everything, so you have all the versions pinned, but then every time you have a new version, a new software, you're going to have new files. So it's basically just duplicated code somewhere, just changing the version number. So limitations on the Spec side, I would say it requires Python knowledge if you want to contribute back with new recipes. And this is while on EasyBuild it's only text files, so even if it's Python in the background, people, they don't know they are dealing with Python when they use the easyconfig files. The other issues, this is one of the main things that we didn't want to switch for Spec. At some point we tried, and our problem is that we were trying to build software and it was not optimized for our system. So for us, it was hard to know if the software it was already tested or not by an expert on our system. So it was unknown. We were building software and then on Cray, Spec has Cray support, but then not every software will use the accelerated numerical libraries. So this is one of the limitations for us. So I said I wouldn't go into details on how to use EasyBuild, so I created a one-slide guide for creating easyconfig files, recipes. So first you need to find the toolchain that you want to use. So there's this command list toolchains. Then if you just go for the popular, you have more chances of succeeding. If you have a very exotic one, you're probably going to move to Spec. So then after the toolchain, you need to choose the easy block. You can always create new easy blocks if you're not happy with the current ones, but basically at CSCS, we try to make simple. We have only 3 easy blocks that we use everywhere, meaning that we don't need to be learning or coding Python or telling the people to tweak with Python for every code. We have some generic easy blocks like configure make or cmake and make, or one generic one that whenever it doesn't fit to the first 2 ones, we go to this one, which is just chaining commands like you would do with bash. And then third step is to find a recipe that is doing a similar thing as you do. So you just typically you just search on the repository by keyword, and then you're going to find a recipe that is doing more or less the same thing, and then you copy paste. So this is not science, this is just best practices. So try to find a software that is doing a similar thing, and then you just adapt to your needs. And finally, you just add the dependencies to this recipe. So this is like one slide. Of course, the framework has many options. Just the help file, the help screen is too long to fit on the screen, so you have more options. This is just to explain how we work at CSCS. So this is example of one of these easyconfig files. So you start with the name of the software, the version, then some metadata, then the toolchain, the version of the toolchain, which will pin the GCC and MPI version, the sources. For common, popular sources, you have some tags, so you don't need to type the URL here. And then the dependencies, and then one section for defining where EasyBuild will check for files just for sanity checking to see if the build was properly installed on the system. So it's just for sanity checking. Okay, so this is an easy config file. So these are the two main things that you need to choose. Now the real examples where at CSCS we use EasyBuild. So the first one was at the installation of the Metal Swiss machine. So we have this Piz cache and Asha with a cray system, and here we have a particular use case where the compiler provided by Cray was not working, so we just used the software stack from EasyBuild. It was faster than opening the ticket at Cray port, so that's in 1 minute, that's the story on how we use the EasyBuild on the Metal Swiss machine. So now it's on production. It's doing weather forecast in Switzerland in production. So it's a 2-cabinet system with one production and the other failover. And this is running EasyBuild. The other main use case is Piz Daint, which is a heterogeneous system. So we have one partition with hybrid nodes and with GPUs and Haswell. So it's the Pascal GPUs and Haswell CPUs, and another partition with Broadwell only. And just to give you some numbers about the system, so it's the number 8 in top 500, number 1 in Europe, and also the second one in the green 500. So just a list of what we have installed with EasyBuild in Piz Daint. I removed all the duplicated versions so that it can fit on the screen. So the latest highlights are TensorFlow and Piano, that we are starting with this new kind of users that typically we had before more HPC users. Now we are moving to also to deep learning. Okay, moving to the last part now. So I was talking about best practice for the users and how to test the recipes and how to deploy. So here's our setup. We have a GitHub repository with all of our recipes, and we have Jenkins CI that is connected to this repository, which is checking every time someone opens a pull request in this repository. Jenkins will check out, will clone the repository, will test this recipe on Piz Daint, and then if it goes well, we deploy on production. So it will be tested on a sandbox, and then if it goes well, it goes to the production. So this is the workflow. So we as application support staff, we create a Git branch with a new recipe. Then we open a pull request on GitHub. Then the feedback process starts. And in parallel, we have here Jenkins that will test automatically the recipe on Piz Daint, and we'll give a feedback directly on GitHub. And in parallel, we have people reviewing the recipes to see if we use the proper version of the software, and to see if people are following the best practices for designing the EasyConfig file. And then once the reviewer passes by the human here and then by the robot here, then the recipe is merged into the repository. So this improves the quality of our production software. This is just to give an example of one pull request. So we have a colleague that submitted a recipe, and then as a detail, he mentioned that he had to change a variable that is not taken in account in the recipe because the build path was too long. So this is a thing that it's not the usual case. So I asked him to add this comment on the easyconfig file so that everyone who takes this recipe in the future will see that if you have a build folder that is too long, then it will fail. So he added the fix. So here the green, I think I have, okay. So the green here means that Jenkins tested and the build passed. So after the second comment, we know that the build is passing. And the review also, I had to approve this, so I approved, the review has passed, and at this point, the change is merged into the repository. So this is how we assure that we don't put in the production things that are not working or not complying with the best practices. So I think I don't have much time. I won't go to the step-by-step guide here on how to set up Jenkins. I just add this for, since you're going to have the slides, and if you want to set up the Jenkins so to do the same, then you can just follow this step. So we will explain you how to set up Jenkins and connect with GitHub. So this is the part where you set up the project. So first you set up Jenkins to connect to GitHub and to test the builds on your system. Second part is to create a project that will use this new slave and it will test your pull requests. So I won't go into details here. I think this is just in case you want to reproduce the setup. So the setup is just one idea. You can replace these are 3 building blocks: GitHub, Jenkins, and EasyBuild. You can easily replace EasyBuild by Spec, of course. If you work at EPFL, you're going to use Spec, not EasyBuild. Then you can also use Travis or something else. So this is just to share the idea. And then I give you some links about the documentation of EasyBuild, the Twitter account for EasyBuild, and our production repository if you're curious to see how our recipes look like and how the workflow is doing in production. So you can just open the pull request and see how we work. And with that, I think that's all. So thank you.